Hello, everyone. This is the 5th day of GeoRamadan Webinar and the last day. So we will start with Dr. Mohamed Mansou. Dr. Mansou is an assistant professor at Cairo University in Egypt and postdoctoral associate at University of Western Ontario, Canada. Dr. Mansou has over 4 years of practical experience and 7 years of research and teaching experience in geotechnical engineering field. His experience comprises the design of shallow and deep foundations, design of earth-retaining structure and shoring system and slope stability analysis, and numerical modeling. So we will start with Dr. Mohammed.
Thank you, Mahmoud, for this kind introduction. Hello, everyone. I hope everything is going well with you. We will start today. I'm going to give you an introduction or a quick presentation about grouted helical piles, new approaches in the installation of grouted helical piles, actually. So first, we will start with our agenda. So I will give a small introduction about the helical piles, its advantages and its drawbacks, the motivation and the objective of developing new grouting techniques for grouted helical piles. I will describe new and existing approaches for grouted helical pile construction, and we will end up with some summary and conclusions. So first, what is helical piles? As we can see, helical piles consists of cylinder steel shafts connected to one or two helical plates, or even more. We can do 3 or 4 helical plates. It can be installed into the ground by applying mechanical torque to the pile head. So we can apply mechanical torque here, and the helix takes the pile down. We can add extensions to the leading section. So we can add extension here, here, or here until we reach the required depths. The helical pile capacity can be calculated as the shaft resistance plus the capacity of the leading section. The capacity of the leading section here can be calculated using one of the two methods here. Either the individual plate bearing method, so each plate acts individually, develop bearing resistance, or cylindrical shear method. So the two helices and the soil enclosed between them acts as a cylinder. We have a friction resistance in the cylinder and bearing resistance at the lower plate. So what will make the pile behave as individual bearing or cylindrical shear behavior? This actually depends on the ratio between the interhelical spacing here between the helices and the helix ratio, as well as the soil, the type of soil we are in, like the piles are installed in. So for soft clay or sensitive clay, if the ratio between the interhelical spacing and the helix diameter is 1.5, this is enough to develop individual bearing. However, for sands, individual bearing can be observed at 3 helix diameter. So if the interhelical spacing over the helix diameter is 3 or more, we can observe the individual bearing. If it is less, we will observe the cylindrical shear. So what is the advantage of helical piles? Helical piles is very popular in North America because it has high axial resistance due to the presence of the helices, especially if it acts as individual bearing. So every one of these helix develop a bearing resistance. It can support inclined load. It is very easy to installation, especially in very limited access areas. It has low levels of noise and vibration. So compared to the driven piles, the level of noise and vibration is like negligible. And it is very actually quiet because we are just like rotating the pile or applying torque to install it. One of the very big advantage also, it allows immediate loading open construction. So in contrast with the concrete piles, in concrete piles, we have to wait for 28 days until we can load them so that the concrete can be cured. However, for the helical piles, once we install, we can apply the load directly to the pile, which make it very useful if we are going to deal with like some existing foundation problems. So If, for example, like there is a differential settlement in a building and we want like to treat this problem, we can install helical piles below the footing, which is excessively settled, and this will help us to solve the problem. It also provides a kind of quality assurance, because when we measure the installation torque, we can use some capacity to torque correlations. So you can expect actually your pile capacity once you install it without the need to do pile load test, just by monitoring what is the installation torque at these depths, and then use some correlations to correlate this installation torque with the pile capacity. And the other thing, it is very also cost effective. So what is the drawbacks of the helical piles? So the rotation of the helical pile inside the soil causes some soil disturbance during the installation. And this soil disturbance affect the contribution of these resisting elements. So because of the disturbed soil, we have a reduced shaft resistance. We might have a reduced end-bearing resistance for the upper helix, or like the cylindrical shear also might be affected due to this shaft resistance. Beside, we have low shaft resistance, low buckling resistance, and the low lateral loading capacity. Because as you can see, the helical pile here has a very cylinder shaft resistance. So like this shaft resistance can be as low as 4.5 inches, which is like slightly greater than 10 centimeters. There are, of course, like some large diameter helical piles, but the popular ones are those within from 4.5 inches to 10.5 inches. So we have like small diameter, which will decrease the resistance of the shaft, the buckling resistance of the shaft, and the lateral capacity of the helical pile. Besides, if we are going to like deep depths, we are going to add extensions to the pile, and these extensions need to be connected with some coupling joints here. These coupling joints are not completely rigid, so under high compression load, we might observe some like lateral displacement due to the incomplete rigidity. Besides, as we know, most of the helical pile capacity is driven from the bearing resistance of its helical plates. And the bearing resistance require high displacement level to be fully mobilized. So probably about 10% of the helix diameter, or maybe like from 5 to 10% of the helix diameter. So these are large displacement level. And usually we don't allow this high displacement level in our designs. So what is the motivation and the objective of what we are of the grouted helical pile? Why people think we need to fix like these drawbacks of the conventional helical pile? So we need first to overcome the drawbacks of the conventional helical piles. We need to improve the soil within the disturbed zone due to the pile installation. We want to increase the contribution of the pile shaft resistance to the total pile capacity. We want to increase the bearing resistance of the helical plate if we can, because it represents most of the pile capacity. We can enhance the helical pile performance by reducing the total settlement at the required design load. So how we can achieve these objectives and motivations? So people think about, okay, we can use grouted helical pile. So grouted helical pile was introduced as an alternative to overcome the drawbacks of the conventional helical piles. There are several existing techniques to install the grouting helical pile nowadays. So the most famous one are the pull-down micropile developed by Chance, and the magnitude helical grout pile developed by Magna. These are very big piling companies in North America. So for a chance, they decided to add like these displacement plates here to the pile helix, to the pile shaft. And while rotation, the displacement plate here create a cavity around the pile shaft. And this cavity was then filled with neat cement grout by pouring, like pour neat cement grout into these voids to form a grout column, as we can see here. Like, it's like the same concept is nearly used by Magnum, but like the place of the displacement plate, instead of adding an additional plate here, they just set a displacement plate between the pile helix as this one. So once the pile is rotated, like this displacement plate also create a cavity around the pile, and this cavity is filled with the neat cement grout to form the grout shaft. However, also Magnum add what is called bending grout propellers. Like the advantage of these propellers is it makes like the board grout and force it to go down, and this will improve the structure of your grout shaft. So you make sure that all the voids is filled and you don't have any gaps, which might reduce the structure capacity of your grout shaft. So these are the existing techniques. However, we thought about why we don't use like more advanced techniques. So now there are two techniques were recently developed of the grouted helical piles. So grouted helical piles using permeation grouted and pressure grouted helical piles. Both of these methods will allow a significant increase in the pile capacity compared to the conventional ones. So how we can install like, or how we can use these two techniques for. So first, like grouted helical piles using the permeation grouting. So in this method, we were in the middle of a project. Actually, we were testing a group of micropiles, consists of 4 micropiles. Actually, we were doing a pile load tests on them. And in order to apply compression loads to the pile group, we need like some reaction piles to take the uplift resistance. And in the middle of the test, we noticed that like these piles are like subjected to failure, and increased uplift displacement was observed without like, and we didn't reach the required compression load to the micropile group. So we thought like, how can we increase the capacity of our reaction piles here? Unfortunately, we were already designed the piles, and the piles was manufactured with 4.5 inches shaft diameter and 12 inches helix diameter. So if we are going to use larger piles, so we have to like throw these away and just manufacture new ones with larger capacity, or larger helical diameter and larger shaft diameter. Like this was like, from the cost wise, was not an acceptable solution. So we thought, okay, why don't we create like 8 holes around the pile helix, and through these 8 holes we are going to inject grout using microfine cement. What is the microfine cement like? Compared, like the ordinary Portland cement can't permeate through the soil voids, especially if it has like some silt components. So the amount of silt, or if the voids are very small, the permeation or the movement of the ordinary Portland cement grout into the voids will not be okay. So we used what is called microfine cement. It has a much smaller cement particle size. And in order to inject the grouts through these holes, we use a fixed head pneumatic packer. So this fixed head pneumatic packer goes inside the hollow helical pile shaft, and the mixer here like start mixing the microfine cement with water at water cement ratio of 0.5, and start pumping the grout through like in lines here, and this fixed head pneumatic packer do the extra rules which push the grout inside the hollow pile shaft and through the pile helices into the surrounding soil. We also add a volume and the pressure gauges in line here so that we can measure what is the amount of the injected grout and what is the injecting pressure. So we observe a huge improvement in the helical pile uplift capacity actually. So for the ungrouted pile here represented in gray and the black load displacement curve represents the grouted ones. As we can see here, we observe an improvement in the uplift capacity with 40%, 47%, up to 80% after injecting 32 liters of grout, 50 liters or 75 liters of grout. So what is the reason of this improvement? So we dig around the pile and extract it, and we found that there is a bulb of grouted sand is created around the pile helix, as we can see here. Like this grouted sand bulb has a higher mechanical and shear strength parameter, which improve the bearing resistance of the pile helix. Besides, also like the helical pile start to fill the gaps created between the pile shaft and the surrounding soil. And by adding like a thin layer of grout here. So like this thin layer of grout improve the friction resistance at the pile soil interface. So now both of our shaft resistance and the helix resistance was improved during this technique. So the other new technique is called the pressure grouted helical piles. So now the market is witnessing a rapid advance in the micropile industry and the pile grouting technology. So the micropile is characterized by its very high grout ground bond or very high shaft resistance. So we thought, why don't we mix between the helical pile advantage and the micropile advantage and provide the market with the super pile, which has high shaft resistance similar to the micropile and high bearing resistance similar to the helical pile. This idea was developed by American pile driving equipment. So basically they add some nozzles here around the pile shaft, and during the installation of the pile, like they inject a pressurized grout through these nozzles. So we are expecting the creation of a grout column all around the pile here. But like a chance to develop ABI developed this technology, but it doesn't have any design guidelines, or like they don't know even what is the shape of the created grout mass here. So in Western University, we developed an experimental program to investigate what is the pressure grouted helical pile performance in sand. We investigated the shape of the created grout column. So why the pressure grouted helical pile is the super pile? The pressure grouted helical pile has high grout ground bond along the pile shaft, similar to the micropile. It has low displacement level under working loads because now we have a major or a huge shaft resistance, and this shaft resistance is fully mobilized at very low displacement level, as low as 0.5 to 1% of the shaft diameter. The grout column provides additional corrosion protection to the pile shaft material. So if you are expecting to install your helical pile in corrosive soil, so by adding this grout column, you provide a kind of protection against corrosion. The grouted shaft also makes the connection between the coupling joint more rigid. The injected grout provide a kind of also lubrication to the helix. So during the installation of the helical pile, the helix is actually face some resistance or some rotational resistance from the surrounding soil. So by injecting this grout, it acts as a lubrication, which will decrease the friction between the pile helix and the surrounding soil, which will reduce the required installation torque. Besides, by increasing the pile shaft diameter with this additional grout column, we increase the lateral pile capacity of the helical pile. But as I mentioned previously, we don't know exactly how the pile will behave or what is the shape of the grout column here. So we conduct an experimental program at Western University on a series of model helical piles, like small piles like this one, having 1 meter length. The shaft diameter is 3.4 centimeter and the helix diameter is 15 centimeter. So API use grout nozzles with this shape. But we thought, okay, so what will be the effect of the grout nozzles? Maybe like the grout nozzles will affect the shape of the created grout column. So we used the 3 different nozzles configuration, like 2 nozzles above the helix looking downward, 2 nozzles below the helix looking downward, and 2 helix below the helix but looking upward. The piles were installed in a cylindrical sand pit, like this one here, having a depth of 1.3 meter and or diameter 1.3 meter and depth 1.5 meter. And the piles were installed to a distance or a depth of 0.8 meter. The sand bed was prepared to the required density using the manual compactor. So we conducted these tests in loose, medium, and dense sand, and in order to investigate what will be the improvement in like the 3 sand conditions. Okay, so the grout was prepared using ordinary Portland cement type 10 with water cement ratio equal to 0.45. So we fabricated this special grout tank to store the grout and inject it during the pile installation. So the tank is equipped with a grout inlet. So this is the place where we fill the tank with grout. An air inlet here to apply an air pressure to the stored grout so that we inject the grout under high pressure, which will improve the grout bond. We have a grout valve to control the grouting process, close and open. And we have a pressure gauge here also to monitor the injecting grout pressure. So the grouting took place by applying an air pressure here to the stored grout, and then the grout is pushed through the hollow helical pile shaft and through the grout nozzles into the surrounding soil. The pile was left for 1 week in order for the grout to be cured, and this 1 week was enough to develop about 80% of the compressive strength of the grout or the FCU of the grout. So we found that like 80% is more than enough. We don't need to wait for another 3 weeks because we were expecting a geotechnical failure, not a structure failure. And then we tested the piles under uplift and compression loading to see what is the difference in the performance between the conventional helical pile or the classical helical pile and the pressure grouted helical pile. So for the first nozzle configuration, which is 2 nozzles above the helix looking downward, when we extract the pile from the sand bed, we observe the formation of a solid grout column. This solid grout column has a 10 centimeter diameter along the pile shaft. And the creation of this grout column can be attributed to like the rotation of the pile allows these two grout nozzles to create a cavity around the pile. This cavity, the cavity diameter was approximately like 7.2 centimeter. However, because the grout was injected under high pressure, the injected grout expands the cavity diameter or allow kind of cavity expansion. Thus, the total diameter became 9.7 centimeter. And this increase in the helical pile capacity is also observed in the micropile industry. And the enlargement factor, which is the ratio between the created or the shaft diameter and the created diameter by the drilling bit is about 20 centimeter. We observe a kind of 26% in as an enlargement factor. So like 9.7 divided 7.2 will nearly give you like 26% enlargement factor. As we can see here, when we test the pile under uplift loading, like the blue load displacement curve represents the pressure grouted helical piles, and the green ones represent the classical helical pile. We found that the pressure grouted helical pile has lower uplift resistance. However, at design load, the ultimate helical pile capacity is fully mobilized at low displacement level. So its full capacity is normally developed at 2 millimeters compared to the classical helical pile, which need up to 8 millimeters to be fully mobilized. So this can be explained by the behavior of the pile itself. So the classical helical pile still acts as a bearing pile. So when you pull it out, like the helix resistance, like the pile helix is actually the main or represents the main resistance. So it is a kind of a bearing failure which need high displacement level to be fully mobilized. However, the pressure grouted helical pile is a friction pile, which explains the full mobilization of each uplift resistance at low displacement level, and also explain the decrease in the pile resistance or the plunging failure occur after that. So as you can, once we reach the ultimate resistance, we start having a plunging failure. However, for the compression load tests, we observed that the pressure grouted helical pile has a much higher, like 72% higher compression resistance due to, as you can see here, like this is the contribution of the pile shaft. So the pressure grouted helical pile has a much higher pile shaft resistance. For the second nozzle configuration, we observe a very interesting, actually, grout shape. So the second nozzle configuration has where like two nozzles below the helix looking downward. We observe the formation of a continuous spiral grout column around the pile helix. The spiral grout column has the same diameter as the pile helix. So this can be explained by the injected grout or the grout nozzles here create the same cavity around the pile shaft, similar to the configuration one. However, now the helix, the injected grout also fill the gaps or the voids created by the pile helix, which explain the spiral shape here. We also observe 6% decrease in the uplift capacity, so it's nearly 7.5 kilonewton compared to 8 kilonewton for the conventional helical pile. However, it is also like the uplift capacity is fully mobilized at much lower displacement, so nearly less than 2 millimeters. For the compression capacity, we observe an increase of 1.19%. So yeah, a very, very huge improvement in the compression resistance due to two reasons. First, we significantly improve the contribution of the pile shaft here, and the injected grout also improve uh, the end bearing resistance of the bearing soil. So the injected grout at the end of the installation will permeate through the voids of the supporting soil and provide a kind of cohesion. Like the injected grout act as a glue which glues like the soil particles together and provide a kind of additional cohesion to the supporting soil, which improve its end-bearing resistance. Similarly, the third nozzle's configuration has a solid grout column, but with a larger diameter now, like it's 17.6 centimeter. For this configuration, we observe a 20% improvement in the uplift capacity. So we reach 10 kilonewton compared to 8 kilonewton to the classical helical pipe. And the compression resistance was like tripled of the conventional helical pipe due to the improvement in both the shaft resistance and the bearing resistance. So as a comparison between the piles, so for the uplift capacity, the ungrouted pile or the classical helical pile has 8 kilonewton compared to 5.8 for the configuration 1, 7.5 for configuration 2, and 9.6 for configuration 3. For the compression, the classical helical pile has 18 kilonewton compared to 31 for configuration 1, 39.5 for configuration 2, and 55 kilonewton for configuration 3, as we can see here. So the shaft resistance, the unit shaft resistance FS for the classical helical piles, it's almost zero because like the pile has very low diameter, so it's 3.4 centimeter, and also the pile was very, very smooth. So like the strain gauges attached to the pile shows nearly zero unit shaft resistance. However, the shaft resistance for the bearing pile range between 40 kilopascal and 50 kilopascal due to the high ground bond and the creation of this grout column or grout shaft. The unit end bearing resistance, which is the end bearing resistance of the supporting soil, also for the classical helical pile, it's 1019 kPa. It's slightly increased to 1132 for pressure grouted helical pile 1, and it's further increase under pressure grouted helical pile 2 and further increase and under grouted helical pile 3. This increase observed in the 3 pressure grouted helical pile can be attributed, as I told, to the permeation of some grout at the end of the installation, which fills the voids of the supporting soil and provide an additional cohesion to its parameters or properties. So we will end up with the summary and conclusions here. So we developed actually 2 innovative techniques for grouted helical pile installation. We introducing permeation grouting techniques in the helical pile installation show very promising results. However, we still actually need more research because like we did this on a very limited number of piles. So I believe it was 8 piles. We used a variable grout, injecting grout volume and different grouting pressure. However, we observe a kind of the creation of the grout sand pulp or the grout sand pulp was not uniform. Like for some of them, we observe like non-uniform shapes, which I believe because like grout always try to move toward like the easiest path. So and the soil is not a homogeneous material. So if some of the grout nozzles face more resistance due to the high percentage of fines or high percentage of salt, maybe. They will tend to move through the other holes. So like further research is still need here to make sure that we understand or we fully understand the behavior of the permeation grouted helical pipe. So the injected grout fills the gaps and increase the friction resistance at the pile soil interface. And it also form a kind of grouted sand bulb around the pile helix, which increase its capacity. So the increase in the total pile capacity, so we observe an enhancement in the total pile capacity by increasing the injected grout volume. So the more grout that you inject, the higher capacity you can expect. For pressure grouted helical piles, the injection of pressurized grout during the installation of helical piles create a continuous grout column along the pile shaft. The shape of this grout column actually depend on the nozzle's configuration used for the grout injection, as we observed. So pressure grouted helical piles has higher shaft resistance and higher end-bearing resistance than the conventional helical pile. So the increase in the QS is attributed to two main reasons. First, the larger shaft diameter. So now the shaft diameter has a larger diameter than the conventional helical one. And also the higher friction resistance at the biosoil interface, because like, as we can see, like the injection of the grout under high grouting pressure increase the radial or the lateral stresses around the pile shaft. And also the delta, which is the interface angle between the soil and concrete, is higher than that between grout and steel, or soil and steel. Okay, so the nozzle's configuration was found to have a minor effect on the pile soil interface. However, it affects the pile shape, as we mentioned. Increasing the unit, the bearing resistance is attributed to the larger to diameter or the higher FB unit and the bearing resistance of the supporting soil. So the increase in the FB is attributed to the grout dissipation into the soil voids. From the comparison between the three nozzles configuration, we recommend using the third nozzle configuration, which is the third, the one that has two nozzles below the helix looking upward. And like this nozzles configuration give the largest pile diameter, so it was 17.6 meter compared to 15 for the second configuration and 9.7 for the first one. So this increase in the pile diameter make it the ones that with the highest pull out and compression capacity. And also the position of the nozzles when it is looking upward, it decreases the possibility of getting blocked during the installations. So for the second nozzle configuration, when you have your nozzles looking downward, sometimes we observe a kind of nozzle clogging and the injection or the grouting process can't be performed. So the third configuration has much lower clogging susceptibility. So, thank you. Any questions?
Thank you, Mohammed, very much. It's very interesting results and lectures. So anyone have a question related with that?
Hi, Mohammed. It's
Hi,
nice to hear you today.
Hi.
So I have like two questions. Like the first question is there any limitation, as you said in the summary, that more grouting you or more pressure you implement on the soil through the helical pile, the capacity will be more. Is there any limitation for the pressuring or for the grouting? Because I think like after a specific point there will be like bludging or like I can't pressure anymore in the soil.
Yeah, for sure. Like there is a kind of a limiting pressure depending on actually your overburden stress or the depths of you are doing your grout injection. So like, yeah, this has been taken into consideration. But usually, if you the general what is used now in the micropile. So for micropile type B, maybe they are using pressure between 0.5 to 1 megapascal, and like this is generally safe for most of our geotechnical like usage or a geotechnical design. If you have a kind of like very loose material and you are injecting grouting at shallow depths, yeah, maybe you have to decrease your grouting pressure.
Thank you. My other question is related not to the conventional helical pile. It's related to the conventional like drilled pile, reinforced concrete pile. According
Okay.
to the amount of effort that has been considered to create like a grouted helical pile, why can't we consider like just a reinforced pile? Because I think like you are just trying to increase the skin friction of the helical pile.
It's not only the skin friction. So if you can, we can go here. Okay, so just imagine if we have two helix or three helix, okay,
Yeah.
and then you start injecting your
There is a problem with the internet, Mahmoud, right?
No, I think with him, with his internet. Yep.
Yeah, okay.
Yeah. Mohammed. Mohammed.
oh yeah, there was an internet interruption.
No worries. Yep.
Okay, so as I told you, first, like there is advantage for the helical pile. One of the advantages is the ability to do it in in very limited access areas. So, which is not like this advantage is not available in the conventional concrete piles. In addition, as I mentioned, just imagine if we have three helices here, and we start grouting or we create our nozzles from the
Like,
third
can you share
helix.
your presentation, Mohammed? We can see it.
Yes.
Oh, I'm not sharing it.
No.
Okay, sorry for that. Yeah. So yeah, just imagine if we have three helices here and we create our grout nozzles on the top helix here. So we will have a shaft resistance, okay, a much higher shaft resistance actually. So the unit shaft resistance for for micropiles is much higher than the conventional concrete piles. Besides, we still have the bearing resistance of the three helices. However, for the conventional concrete piles that you mentioned, we only have shaft resistance along the shaft and bearing resistance at the pile too. So the pressure grouted helical pile will allow you to improve the unit friction resistance of the shaft because it is injected under high pressure. So you are expecting higher unit shaft resistance than the conventional concrete pile. And it gives you the possibility to add more helices, which will add to your end bearing contribution as well.
Like, thank you very much. Like, that's answered my question.
Okay, thank you.
Perfect. Any other question? Thank you very much. It was like a very interesting lecture. Thank you.
Thank you, Mahmoud.
Thank you.
Bye-bye.
Bye. Okay, so we will move now to another lecture. It is a presentation from Menna Farag. Menna is a civil engineer now, a technical engineer at Nile Water Sector, the Ministry of Water Resource and Irrigation. Menna obtained her master in water resources and hydraulic engineering from Banha University and her baccalaureate from Cairo University. So Menna, go ahead anytime.
Assalamu alaikum, everyone. It's my pleasure to be here. Well, let's start.
Yes, could you share your screen?
Yeah, I'm doing that now.
Perfect.
All right. The topic today will be about transient flow simulation, analysis, and protection of pipeline systems. I guess that most of you guys right now wondering how this is related to geotechnical. Well, let's see, okay? One of the most common geotechnical problems is soil settlement. What is soil settlement? Soil settlement is a soil downward movement in the vertical direction, typically induced by stress changes. Well, there are three major causes of soil settlement, and they are drying and shrinking of the soil, poorly compacted fill soil, and wetting and softening of the soil. Well, about drying and shrinking of the soil, during prolonged dry periods, the soil may become too dry and start to shrink, and consequently, when the soil dry, it creates void between its particles. And when this happens under certain loads, the soil will be settled. And the other cause, poorly compacted soil. Well, if the compaction of the soil is not done or done poorly, and of course under certain loads, this may cause the soil to be compressed, leading of course to the soil settlement. And the third cause, and it is wetting and softening of the soil. Well, water can pose dangerous for foundation in several ways, such as flooding, heavy rains, and broken water lines. When clay soil contact with water, it will weaken its load-bearing capacity, causing, of course, soil settlement. The topic today is about a specific point why broken water lines happen. Okay, there are a lot of uncountable reasons for broken water lines, but today I will talk about a very famous but not so recognized phenomena, and it is water hammer, hydraulic shock, transient event, or hydraulic transient. It's really a lot of names describing the same phenomena. Well, let's say give a hint about water hammer. I guess most of you notice it but not recognize it. When you at your house and opening the water tap, maybe sometimes you are hearing like banging noise, right? I guess most of us hear that noise, okay? That's what exactly called water hammer, okay? But it's on small scale. When we are talking about water supplying systems and wastewater systems, it's really getting more complicated and more risky, okay? Let's start to introduce water hammer. What is water hammer? Water hammer is excessive pressure that will happen due to sudden change in the velocity, okay? What are the causes of water hammer? Pump startup and pump power failure, sudden valve opening and closing, improper operation or sizing for surge protection devices. Despite that we are putting surge protection devices to control the surge pressure that resulted from water hammer, it just might be cause more harm than good if we did improper operation or improper sizing for these devices. and other factors such as pipe filling and drilling, a changing in water levels in the source or the destination, or a changing in the flow transmission condition, such as if we are transmitting the flow or water through a very hot area or very cold area. Okay? Let's start to describe the events or the causes that might be the result of water hammer. All right. If we have a very typical pipeline system with a pump station, this is a destination, sorry, this is a source and this is a destination, all right? This is a hydraulic grade line, and this is the head that pump pressurized the flow or the water through the pipeline system, okay? It's a system, pressurized system, not a gravity system, okay? When we have a pump power failure, which will lead to a sudden stopping of the pump, then we might note that the hydraulic grade line become under the profile of the pipeline. What does that mean? That means that we have a negative pressure, all right? And do you know what that indication for? That indication for that the flow or the water is turning into vapor, okay? Well, what will happen when we will return the power and the pump gonna start up? There is a very famous phenomena that combined with this simulation and this process of pump power failure and pump power startup, and it's called column separation. Okay, let's say we have a typical pipeline system, as we talked before, and unfortunately that pipe system has a high point of its profile. If the process is going peacefully, there's no problems. But what if we have a pump power failure? Okay? If we have a pump power failure, then that will lead to separate the flow into columns, okay? This figure. One is gonna to return to the pump destination and the pump direction, and the other gonna back to the destination because there is no pump to pressurize the flow through the pipeline. It's a gravity system. So the flow gonna be to act under the gravity and separate it to two columns. One is gonna return to the pump direction and the other gonna return to the destination direction. And that will cause negative pressure as we talked before, and gonna be a vacuum here. There's gonna be a vapor. The water or the flow gonna turn to a vapor. Well, when the pump gonna start up, this will lead to the column at the pump direction to move towards the destination column because of the pressurized system. Now the pump is working and it's turning to be a pressurized system. So the column as the pump direction gonna move towards the column as the destination direction. Well, if this column is moving really high velocity, of course, because it's a pressurized system, that will lead to the two columns to collide together and causing pipe rupture and pipe fatigue. Okay? The second cause is sudden valve opening and sudden valve closing. Of course, in the normal operation condition, we can close the valve, we can open the valve, but it has to be gradually opening and gradually closing. What will happen if we have sudden valve opening and the sudden valve closing? There is a very famous phenomena that combined with this operation, it's called valve slam. Okay, when I close the valve suddenly, this will lead to expansion in the pipe and pipe rupture, and the water or the flow gonna make a slamming to the valve, okay? The third cause is improper operation or improper sizing for surge protection devices. Say we have air valve as a protection device. We talked before that due to pump power failure or due to any other cause that might causing water hammer, there will be a negative pressure, and that negative pressure will turn the flow or the water into vapor. Then at this point, I want to put air valve to just extract the air or extract the vapor that will be existing in the system. Okay, let's say I put that valve and I put it in place that really is not the exact place that I need to extract the air here, or I put it with a very large size, or I did the operation of the valve in a very fast term or very fast pattern. What will happen? Okay, the same. If we have a here, and the size of the valve is not proper for the operation, or the operation of the valve itself is very fast, that will lead to the two water columns to collide together and causing gravity for the pipe and for the air valve itself. Okay, where exactly does water hammer occur? As I said before, we all hear the banging noise of the water hammer. Okay, but it's not really risky at our houses. Then when it will be really risky? It will be really risky where the flow or the flow through the pipeline has a sudden or a rapid change in the velocities. And that will be like at the pump stations, air release valves, control valves, and in a pipe longer than 300 meters with high velocities. So if we are talking about the pipe system in our houses, it's not really risky. It's gonna be just a really simple system. Okay, why I'm talking about water hammer, why I'm talking that water hammer need to be recognized and taken into considerations, because it really causes really bad effects, such as system fatigue, a whole system fatigue, ruptures, and if you are transmitting wastewater, it will cause a backflow and contamination. This picture is from hydropower plant in Russia. A whole turbine just move out of its place due to water hammer. And 75 persons passed away because of this accident. It might cause pipe collapse, pipe formation, and vapor cavity. This pipe had been faced a negative pressure. If you face a negative pressure, you find the deformation of the pipe gonna be in such a pattern. If you faced positive pressures, the pipe gonna be explode and be ruptured. And of course, build internal systems such as the T-sections, vents, and of course, valves. Okay. How can water hammer effect be avoided? Before I said how, I want to just describe some equations to just simulate and state the parameters or the character parameters that affect the water hammer. This equation called Jokiewski equation. It's the simplest equation in water hammer. And it works for gravity system mainly, okay? H is the Jokiewski equation equal A, and it's the wave celerity, multiple V is the initial velocity of the liquid. It's the velocity in the continuity equation, the equation that say Q equal V multiple A. V is the initial velocity, A is a cross-sectional area of the pipeline system, and of course Q is the discharge, the flow discharge that's flowing through the pipeline. And G is the gravity acceleration. What is A and what is what are the parameters that affecting the wave celerity? Let me just give you number two, just make it really sensible to understand how is the pressure of the water hammer. The wave celerity might reach to 1,000 meters per second. And if we say we have V with 2 meters per second and G was 9.8, we might have 1,300 meters as a head pressure. Can you imagine the value? It's really high value. And the most significant value in this equation is a value of wave celerity. So we have to know what affects the wave celerity. there is a lot of parameters that affecting wave celerity. And and they are bulk modulus of elasticity, LK, rho is liquid density, D, of course, is the pipe diameter of the pipeline, E is the wall thickness, and E capital is Young's modulus, pipe elasticity, and depends, of course, on the material pipeline. And phi is a factor related to pipe supporting condition, and it's related to U as Poisson's ratio. And I guess you all know it's the ratio that describing the deformation that happened to the material, okay? This is a sample example for pipe supporting condition and how we calculate the phi. Of course, in water hammer, no one calculates manually the heads or the pressure. It's really complicated process, and it's complicated equation. It's, as I said, it's the simplest equation, and it's only working for gravity pipeline. And if you have a pressurized pipeline with pump stations and so on, this equation won't work. So most of the time, or I guess all of the time, we use numerical programs to compute all of these parameters. So for phi, we just enter the pipe supporting condition, and the numerical system will just tell you how the or what the value of A. Okay. All right. Let's talk practically. Okay. There are 3 principal design techniques for avoiding water hammer, and they are alternation of pipeline, such as profile and diameter. As I said before, the problem of high point and how it will cause a bump, column separation. And of course, how the diameter directly affecting the value of the wave celerity. So as much as possible, we can avoid having a high point in our profile. And of course, increasing the diameter, we're reducing the value of the wave celerity. Actually, increasing the diameter will, reduce the value of wave celerity, but that until a certain value, okay? If you're increasing the diameter uncontrollably, this will lead to increasing the weight of water column we were talking about later, and that will, of course, increase the pressures. So you have just to try and just control the diameter in estimated value, not just putting as higher value as you want and assuming that will make you safe against water hammer. No, that won't make you safe, okay? And the second point, improving the process of pump control and valve operating conditions, of course, that we, as much as we can, we have to avoid the process of pump power failure and pump startup. And of course, the process of opening and the closing of the valve have to be gradually, as I said before, not a sudden valve opening or a sudden valve closing. And the third point, and this really important point, design surge control devices. This will be if you have, let's say, a system for supplying water, okay? As normal conditions, we won't have any problems. We won't have a water hammer problem. But as I said, water hammer happen at emergency causes, okay? When we try to put and sizing the control devices, as a beginner, we try to make a simulation for these emergency causes. And after we put a simulation and estimating the value of pressures of water hammer, then we can state what exact control device we can use and what is sizing and what is the proper operation of the control surging pressures. There is a 3 famous controlling surge devices, and they are air vessel, and it's usually using after the pump station, and it's usually using to protect the system against the pump power failure. And the second is surge tanks. Let me just state quickly the difference between the air vessel and surge tank. The surge tank just provides the system with water, all right? But it's water that are applied to atmospheric pressure. There is no pressure. It's just affected by the head of water in the tank, okay? And about the air vessel is affected, it's actually pressurized water, okay? Both systems provide water to the system and allow water to just getting out of the system. We provide water to the system in case of negative pressures, and we just have water of the system or take water of the system in a case of positive pressures. And the third famous device, air valve, as I talked before, if we have a high point, it's without even thinking, we talked about soil settlement and the causes that might right? The causes that might cause water pipeline systems. We talked about the causes and the possibility of water column separation to be happen. And of course, it often occurs after pump power failure as the highest point of the pump pipeline profile. Using air vessel effectively protects the pipeline. And I forgot to say that you can, of course, use a lot of protection devices together. Like, for example, you can use air vessel with surge pressure because, with surge tank, because sometimes it's really high values or higher values of pressures that resulted due to water hammer. And that will result to a very, very high volume of air vessels. For some example, as some water applying system I was working on, I had to bought air vessel with a 400 meter cube, and it's really, really high volume. So I tried to neglect that value and put a surge tank with an air vessel, and that will lead to the reduction of the air vessel volume. And this is the third conclusion I have to take about. And changing the flow density have a great impact on the pressure values. As I said before, the flow density is a very effective parameter in the equation of wave celerity, and that affects directly the pressure values that going through the pipeline. And increasing the diameter of pipeline, of course, reduce the surface pressure, as I said, to a certain value. After that, well, it will increase the pressures due to the increasing of the water column in the pipeline system. And of course, changing the pipe material has a significant effect on the pressure values, as I said before. And thank you for listening. Any questions?
Thank you very much, Menna. It's very interesting presentation. Any question about that? If not, thank you very much.
Thank you.
Thank you. And okay. So Abdelmoneim, are you ready?
Yes, sir. So let's get started.
Yeah.
Sorry, I'm here.
Menna,
Maybe?
can I delay you for like 20 minutes because Farah is now at the iftar time in Dubai. She lived in Dubai.
Oh,
And
okay, yeah, sure,
yeah.
sure.
Sorry, Menna.
No problem, no problem.
Yes. Farah, could you share your screen? Could you hear me, Farah? Perfect.
Can you see my screen?
Yeah,
Oh,
I can
okay.
see your screen, yes. So we will start now with a presentation from Farah Barakat. Farah Barakat is a current geoenvironmental engineering PhD student in Department of Civil Engineering at Queen's University in Kingston, Ontario. She is working under the supervision of Dr. Kerro. Farah graduated with honors from American University in Dubai with a bachelor's degree of science in civil engineering. So go ahead, Farah.
Yes. Good afternoon, guys. So my name is Farah, as I said, as Mahmoud said, and today I will be giving you a quick overview regarding contaminant transport that occurs beneath hydraulic containment applications. So hydraulic containment applications includes any application that has been designed to control the migration of dissolved contaminants or chemicals to the surrounding environment and groundwater. Examples include mine waste covers, landfills, and monofills. So a landfill is a carefully designed structure built into or on top of the ground in which waste is disposed and is isolated from the surrounding environment. Now, the waste contained in a landfill can be of different sources, and typically we can have separate landfills designed for the type of waste that will be deposited in them. So the different sources of solid waste can be residential solid waste, industrial, commercial, and institutional waste, construction and demolition waste, or special wastes, which are typically hazardous wastes. So for residential solid waste, it is typical waste that is generated by our everyday lives and at home, and they include paper, organic wastes from food, plastic, glass, and so on. Industrial, commercial, and institutional wastes. So industrial wastes are wastes that are generated from factories, mills, and refineries. Commercial wastes are what is generated from restaurants, offices, retail, and hotels. And institutional wastes are wastes that come from institutions, so schools, universities, hospitals, and all these places. The third type of waste are construction and demolition wastes, which are wastes from construction, repairs, and demolition of residential and commercial buildings, roads, and bridges. So they include a lot of wood, concrete, asphalt, and drywall, and all other materials that can be used during construction. Lastly, we have special hazardous wastes, and they include anything flammable, reactive, toxic, or explosive. These wastes are usually separated from other types of waste for special treatment and disposal. Now, a typical hazardous waste that we typically use every day are batteries. So these batteries, if you notice, typically they say that you cannot throw them in normal solid waste because they are considered hazardous. So once the waste is disposed in a landfill and it is covered and operational, percolation or infiltration of precipitated water or rainwater through the cover of the landfill usually occurs, which results in the generation of a liquid that will pass through the layers of the waste. Now, this liquid will dissolve through the different contaminants present. This liquid will dissolve the different contaminants present in the waste, leaching out the soluble salts, carrying the biodegraded organic compounds, and suspending the fine particles in the waste, forming a liquid leachate that accumulates on the base of the landfill, where there typically exists a leachate collection system that would take this contaminated water and transport it to be treated. Now, the presence of a leachate collection system is not enough to prevent liquid from seeping down the soil layers present beneath the landfill and so it will result in contaminating the environment surrounding it. So a barrier system is designed beneath the landfill to contain this leachate. This system is usually made up of several different layers, the simplest being a composite liner, followed by an attenuation layer of low conductive soil like the one seen here in the figure. Despite the presence of a barrier system, contaminant transport beneath hydraulic containment facilities can still occur because these systems are designed to mitigate transport but not fully stop it. And I will explain how and why in a bit, but first I want to make sure that you know what do I really mean by contaminant transport. So here you can see a conceptual site or model of the landfill. And this is the lined landfill or the unlined landfill. And you can see the different ways that contamination that happen. So one of the ways is through gas emission. Due to the decomposition of waste, you have arrows coming out from the landfill where these gases are typically toxic, so they can contaminate the air. And another form is downwards through leakage. And this will result in the contamination of the soil beneath the landfill. And if it reaches the groundwater, it will result in the contamination of the groundwater and probably the surface water eventually. So I will focus on contaminant transport that will occur at the base of the landfill. And this type of contaminant transport can occur through different means, which includes advection, diffusion, and dispersion. So when I'm saying the phrase contaminant transport, I'm usually referring to all of these three. Now, advection is simple. It is the movement of contaminants with flowing water, which is moving from high head to low head. Diffusion does not occur due to flowing or moving water, and it is simply the movement of contaminants from points of high chemical potential to points of low chemical potential. So sections with high concentrations to areas of low concentrations. The degree to which diffusion happens for a certain chemical usually differs for different materials. Dispersion is the movement of a contaminant due to local variations in flow. Now, in barrier systems that are beneath hydraulic containment facilities, the hydraulic conductivities of the soil layers are typically pretty low. For example, in Ontario, the maximum conductivity for a soil used for attenuation in barrier systems is 10 to the -7 meters per second. So dispersion will be extremely small. And so in that case, we will not really take it as seriously as advection and diffusion. So when designing a barrier system beneath a certain landfill, we should always take these three forms of transport into consideration. So
Continue, Farah.
Okay. Depending on the critical chemical or contaminant that we are looking at, we should make sure that the degree of contamination and the concentration of the chemical that is detected in the groundwater or aquifer at any time throughout the contamination lifespan of this landfill is always less than the maximum allowable water concentrations of this contaminant that are typically set by the Ministry of Environment of the country that you are in. So now let us look at the basic component of a barrier system, which is a composite liner. So composite liners are typically laid at the base of landfills and containment facilities. They consist of a geomembrane that lays directly on top of a geosynthetic clay liner. But in most of the times, these two layers are never in perfect direct contact. So if fluid is present between these two layers, it has the capacity to move laterally. And a parameter that we call the interface transmissivity is introduced to represent the resistance to fluid flow that exists between these two layers usually. So ideally, geomembranes are impermeable, so no advective flow can develop through them. But the problem is that geomembranes have a high coefficient of thermal expansion. So when they are laid on the field and are exposed to sunlight, they expand and develop wrinkles to accommodate the extra material. In addition, even when we have good quality assurance, holes will develop in the geomembranes, especially in the wrinkles. This especially happens once a layer of cover soil is placed on top of the geomembrane and construction operations are still being performed on top of the liner, so it will damage this geomembrane. So if a hole is present in a wrinkle, the wrinkle will act as a conduit for storing fluids. And due to the lack of perfect direct contact discussed earlier, leakage and flow will not only develop beneath the wrinkle itself, but it will develop along a certain wetted distance beyond the edge of the wrinkle due to the lateral flow that will be between the geomembrane and GCL layers. So the extent of this wetted distance, denoted by A in this figure, depends on the interface transmissivity that we spoke about earlier and the hydraulic conductivity of the GCL. So there exist specific equations that can help us quantify this distance and the leakage that passes through the hold wrinkles in barrier systems. These are the equations used. As shown, the wetted distance A0 depends on the interface transmissivity and hydraulic conductivity of the GCL. In addition, if you look at the leakage equation Q, this wetted distance is a function of the amount of leakage that will develop beneath the wrinkle. So this is how advective transport develops beneath the wrinkle, even if we have composite liners present. Now that we discussed how advection can happen, let's talk a bit about diffusion. Diffusion happens due to a change in chemical potential, so it will occur regardless of whether the geomembrane is damaged or not. To estimate the diffusion coefficient of contaminants that occurs beneath hydraulic containment facilities, such as landfills, for each specific contaminant and liner, there is a specific parameter called the permeation coefficient that allows you, through modeling, to estimate the chemical transport from one side of a material to the other over time. These values are present in the literature for typical contaminants such as benzene and toluene, and their relative permeation coefficients are shown here in the table. But at the same time, for new and emerging contaminants and for contaminants that were not of great interest before, or for new liners that keep getting manufactured over time, these diffusion coefficients are unknown. Thus, in that case, diffusion tests need to be set up to try and estimate these coefficients for these contaminants through different materials and liners. So diffusion tests are done using steel cells like the one shown in the picture here. And these cells have two compartments. Typically, one is bigger than the other. And the bigger compartment is where we put the source, which will be a solution containing the contaminant at a known concentration. And the smaller compartment will contain deionized water with no chemicals or minerals whatsoever. In the center, separating these two compartments would be the geomembrane or film that I want to test to know its diffusion coefficient, or any material really. So one of the very important things you have to consider in this test is to measure, to make sure that the two compartments has the exact same cross-sectional area and are completely filled with the solutions to make sure that no advective transport occurs inside the cell from high head to low heads. So after we set up the test, it will remain running, and I will constantly sample the source and receptor compartments at a typical rate. And these samples are analyzed to know the change in concentration in the two compartments over time. So based on the rate of increase in concentration in the receptor and the decrease in the source, you can estimate the diffusion coefficient by modeling this change on certain softwares. And one of the software that I personally use is called Polyute. So once you reach a point where you detect equal concentrations in the source and the receptor during analysis, that is the point where equilibrium is reached, and that is the point where you can terminate your test. So beneath hydraulic containment facilities and landfills, there will exist advective diffusive transport. So basically, you will have movement of contaminants under the combined action of advection and diffusion. So the movement with flowing water and chemical potential. As a result, you have to make sure that the degree of contamination that occurs along the surrounding environment of such facilities, such as the soils and the groundwater, is acceptable. By acceptable, I mean that it should not reach a degree to which it is harmful to humans or aquatic animal or any form of life. So to do that, we need to first set the main and most critical contaminants that need to be considered in your landfill. So you have to know the chemical composition and which contaminants are the most critical. After that, you have to have the diffusion coefficients through the different layers of your barrier system. So if you just have a single composite liner, then you need the diffusion coefficient of your geomembrane, your GCL, and your attenuated layer of soil. And then you would need to calculate the leakage through the estimated number and length of wrinkles that will be available on your design landfill. And after that, you would use software such as GeoStudio or Pollute to model your full design, which includes the barrier system and the landfill. And these softwares will be able to give you the concentrations in the soil and aquifer over time. So once you have the peak concentrations, if you look at the concentrations, you will be able to figure out what is the peak concentration. And once you have the peak concentrations, you need to compare those concentrations with the maximum allowable concentrations in drinking waters or soils for the specific contaminant you are considering. If your concentrations are below these limits, then your design barrier system is good. But if the concentrations in your modeled in the aquifer or groundwater in your modeled barrier system detected by the softwares are above these limits, the design of the barrier system needs to be altered, and more protective layers will need to be added, such as using double composite liners. So modeling needs to be simulated once a new design option is developed each time, until you get concentrations that satisfy the regulatory limits set by your government. And this is very important to ensure that clean water is being provided to all of the population and to make sure that no aquatic or environmental life whatsoever is harmed. And that is basically it. Thank you so much for listening. If anyone has any questions, please let me know.
Thank you very much. Any question? Thank you, Farah, very much. It's very interesting. Yeah, thank you. Abdelmoneim.
Yes, sir.
Thank you, sir.
Okay.
Wait, I will introduce you first.
Okay.
Abdelmoneim El Naggar is a graduated student at Western University. He obtained his baccalaureate from Dalhousie University. His research focuses on studying the effect of ground movement of RC structures. So go ahead.
Thank you for the introduction, Mahmoud. I know you're all fasting and some people are approaching Maghrib, so I'll try to keep this as short as possible. Okay, so today we'll be talking about the, can you see my screen first of all?
I can. Yes.
Oh, yes, okay. So today we're going to be talking about the effect of foundation settlements on reinforced concrete frames. So first of all, let's talk about the different types of settlements that we might experience within a structure. So we have three main patterns. So the first one is basically when you have a uniform settling of the whole structure. You usually won't find any structural damage within this uniform settlement. Now the second type, which is dangerous, is tipping settlement. So here you have a differential settlement of the soil strata. However, your building is stiff enough to not have any cracks, basically. So you'd have a tilting action. And the most codes basically have a limit for this tilt. Then finally, we go to differential settlement. So this is one of the most damaging of all, basically. And it's where your building settles differentially. So the foundation itself would move in a different motion with respect to the other footing, for example. Okay. So differential settlements, why do they occur? Well, differential settlements basically occur from an uneven relaxation of the stresses within the soil strata. So this uneven relaxation would cause displacement, basically, and a trough settlement pattern, which we see as differential settlement. So this ground movement or this settlement would give you a new stress scenario that you would have for pre-existing structures within the area, basically. And so your buildings, you weren't designed for these new displacements. And because of that, you could basically be exceeding your own structural design capacity, which could result in serious damage, as you can see over here. So differential settlements, it could arise from several activities, as for example, the change in moisture content, liquefaction, seismic activity, vibration within the soil particles, and construction activities like tunneling, for example. So over here, the Leaning Tower of Pisa, this is one of the most famous cases of differential settlement. So the Leaning Tower of Pisa was built on soil containing clay and fine sand, and it had a high level of groundwater. However, it experienced differential settlement and a tilt, as you can see here, because of the increased deformability and compressibility of the southern part of the tower, the soil under the southern part of the tower, with respect to the northern part. So this is one example of differential settlement. Now, another example here could occur due to tunneling. So the ground movements propagating from an excavated tunnel opening would result in vertical and horizontal ground displacements, as we know. And so basically when you have, when these displacements reach the topsoil strata, settlement troughs are created, new strains are introduced and could produce damage, as you can see over here. So these photos are of a medical facility in a place called GeoRamadan. I hope I'm pronouncing this right. It's in Turkey. Okay. So differential settlements, their effects have been studied empirically, analytically, and numerically throughout the last few decades. Early empirical approaches aimed at developing design limits for these settlements and for the maximum limit, basically, that that a structure could experience without having any nonlinear effects or damage. So later on, it became evident that the empirical methods do not really give you a full picture. It gives you a partial solution, which is when two researchers, Skempton and McDonald, in 1956, they were able to quantify the maximum allowable settlement. This was basically the first of its kind in terms of differential settlement quantifying. And this was based on surveys developed from, it was basically an analytical study of the 58 buildings that experienced differential settlement but did not experience any damage, and over 40 buildings that suffered various degrees of damage. And they proposed a limit that was validated ever since. And this limit basically, it considered the settlement of the structure due to its own weight, and the performance was correlated with something called the angular distortion. So the angular distortion, this is a geometric ratio, basically. So it is a ratio of the settlement between 2 points within a structure to the distance between these 2 points, the horizontal distance between these 2 points. And if you look in most codes right now, like the Spanish code, the Canadian code, all of these codes, even the Euro code, I believe, you'd find that they're given in terms, the limits are given in terms of angular distortion. Okay. So these are some of the most notable angular distortion limits proposed in literature, basically. So you have Meyerhoff in 1947, Skempton, we already talked about him, Paul Shinokar, and the National Building Code of Canada. So the National Building Code of Canada, it says that you would experience structural damage at a ratio of 1 to 250, but when you reach 1 to 150, you're going to experience ultimate damage, or material damage, basically. So something greater than the cracks. The American Concrete Institute gave you a flat benchmark of 20 millimeters that you cannot exceed of the settlement. Okay. So on to objectives. So the objective basically of this study was to analyze reinforced concrete frame structures, model them using the finite element software, and study their effects, the effects of the span height and height on the structural performance of that frame structure. Then we would take that structural performance and we would assess it and compare it to the damage limits that are already there in literature. Okay. So basically, our reinforced concrete frame elements were modeled using elements in ANSYS called the CPT 215. This is an 8-node coupled pore pressure solid element, as you can see over here, that basically supports free smooth surface cap microplane yield function. So what do I mean by that? Instead of using normal stress strain relationship, I used a material model that allowed for tension caps and compression caps. And this was better in terms of providing a more stable numerical solution for implicit finite element algorithms. And it was also less dependent on the mesh and more accurate. So that's why it was chosen. So some of the special features of this element is that it allows for large deflections, it allows for large strains, and a better stress stiffening. So it's basically able to capture the triaxial behavior of the concrete. Okay, now for the transverse and the longitudinal reinforcement, it was modeled using discrete elements, as you can see over here, that is suitable for simulating reinforcing fibers, including plasticity, stress stiffening, and large deflections. A perfect bond was also assumed between the concrete and the reinforcement. Okay, so now we went on to validate our model. So to validate our model, we chose experimental data from Yusuf et al. So Yusuf, actually Dr. Yusuf is my supervisor at Western. We had only 10% difference between his experimental data and our ANSYS simulation. We went on to validate it with another data, basically from a researcher called Harish. And we obtained 9.6 in ultimate displacements. So we were able to assume that our model is basically able to capture the nonlinear behavior accurately, and we went on to develop our own model. So several reinforced concrete frame structures were detailed and designed according to the Canadian standard, the CSA 23.3, the Red Book. And so basically over here, as you can see, this is a detail of the reference frame used, 4.85 meters. And so the loads that were included within the design, basically, were the frame's own weight and a 200 millimeter thick concrete slab on top of this frame, along with a live load of 1 PPA as given to us by the NBCC, the National Building Code of Canada. So as you're going to see later on, we studied the effect of the beam span by modeling spans of 3 meter, 4.85, 7, and 9.7 meter spans. And the steel reinforcement was adjusted for each span, basically, to maintain the same demand versus capacity ratio, and in order to give us more consistent comparison. Okay. So the frame was assumed fixed at one end, while the other end, a displacement control load was applied to simulate the differential settlement. And this frame was basically loaded to ultimate failure in order to capture the full non-linear behavior of the frame. And I know you wouldn't, so let's go back here. I know it is not really practical to have a 200 millimeter displacement. However, I just put that to get the ultimate material failure. So I know, yeah, 200 millimeter, it's like, it has to be a very severe case of differential settlement. Like I think even the B2 in Frankfurt, when they were doing the B2 tunnel, I think it was only 170 millimeters at the maximum area. So I know these loads are a bit exaggerated, but it's to capture the full nonlinear behavior of the frame. Okay, so now on to the results section. So as I said before, the effect of the beam span on reinforced concrete frame structural performance with respect to differential settlement was done through 3 meter, 4.85, and 7 and 9.7 meter spans, as you can see here. In this slide over here, we are showing the normalized moment versus settlement curves for each span. The moments here are normalized according to they're normalized against the factored moments induced by the dead loads and the live loads acting on the frames. As you can see over here within the graphs, it is evident that larger span frames can accommodate larger deflections as compared to shorter spans. So then the differential settlement effects are more prominent in shorter spans, basically. So as you can look over here, the differential settlement required to produce a first crack in the reinforced concrete frame for 3 meters. And by the way, I am saying the first crack, I am defining it as a yielding settlement. So the load or the settlement needed to produce the first crack, I call this as a yielding settlement. And in the 3 meter span, it increased by 60% when we increase it to a 4.85 meter span. Okay. So we increased from 8 millimeters to 20 millimeters of differential settlement. Likewise, the ultimate failure, where the material failure occurs of the frame, increased by a twofold, from 26 to 60 millimeters when comparing the 3 meter span to the 4.85 meter span, so here to here. And as you can see, basically, the larger the span is, the more ductile the performance is. So as you can see, basically, the larger the span is, the more ductile the performance is. Now, here you can see the yield and ultimate settlement trends for varying span widths. So as we see, the settlement required to produce the first crack increases almost by threefold from 4.85 to 7.3. So this is only a 50% increase in span. Okay. So the ability to accommodate for distortion and increases and ductility is improved, as we said. And this is a comparison of our settlement tolerances to the actual yielding settlement obtained. And again, as we said before, the yielding settlement here is the needed to produce a first crack to throw you into the nonlinearity region. Okay. And so if we look at the 3 meter span and 4.85 meter span, we're going to find that the Poultrin and Tokar and the Scampton and McDonald limits, they fail. So the Scampton fails by 32%, while the Tokar limit fails by 18%. So it fails to give you a conservative estimate. Okay. And if we take a look here at the National Building Code of Canada, it gives you a better estimate, actually, and it's actually one of the better or among one of the most conservative limits. However, if you look, for example, at the ACI, the American Concrete Institute, at certain areas, it's very clingy. Like you're basically you're right within both values, so it's not really conservative over here. So this, if you're designing, for example, and you're at the limit over here, you're playing for your luck, basically. So over here, we can see the damage profiles. So the tensile damage, as expected, is most concentrated at the fixed column at the lower portion. So this means that the column experiencing a smaller settlement, like with respect to its other end, would be the one that would experience greater damage. So at shorter spans, the developing damage becomes concentrated towards the upper portion of the column, experiencing the greater settlement and the adjacent beam. And this damage becomes less and less critical as the span increases, which is why frames, as we said before, with longer spans tend to tolerate a greater degree of differential settlement. Okay, so we have the same study with frame height variation, as you can see over here. And we normalize the moments against the normal moments that would be obtained from the dead and live loads. And as you can see over here, as expected, the height increases the ductility and it allows the frame to withstand greater differential settlements. So shorter frames would be more prominent to damage than longer ones. Over here, this is a comparison of the yield settlement and the ultimate settlements. So again, same thing we said before, angular distortions are higher for higher columns. So you're able to go for further and accommodate further displacements, basically. And yeah, over here you can see the damage profile. So now we can go on to conclusions, basically. So from this study, we found that certain limits used by codes, like the ACI, for example, are not conservative when it comes to shorter spans. And they do not really, these limits do not include the effects of the geometry and like the moment of inertia, basically, and the material properties. So in order to give a more accurate or a more conservative limit, you would need to develop a limit that would include these effects. Okay. So thank you for listening to my presentation, and I hope you enjoyed it.
Thank you very much. Very good presentation. Thank you.
Thank you.
Any question? If not, thank you very much, and thanks to all that attending and joined to your Ramadan webinar series. And see you next year, inshallah.
Inshallah. Thank you for hosting this.
Thank you very much.
Thank you.